Hello everyone, welcome back to NPTEL lecture series on cycloaddition reactions. In the last 8 lectures, we have been talking various aspects of Diels-Alder reaction. In the last lecture, we talked about Alder-Rickert reaction, retro Diels-Alder reaction and dehydro Diels-Alder reaction. So today's lecture, we focus mainly on the use of Lewis acid in 4+2 cycloaddition reaction and also on asymmetric Diels-Alder reaction. So normally what we do when we do a Diels-Alder reaction, we simply heat it in a solvent or in a sealed tube. Okay, so sometimes you have to heat it at very high temperature, but if you use Lewis acid, the Lewis acid can in fact bring the energy gap between the LUMO of dienophile and HOMO of the diene. Okay. So when the energy gap decreases, automatically the reaction can be done at much lower temperature. It can be done at room temperature or it can be done even at -78 degrees. See what happens when you add a Lewis acid. For example, if you add a Lewis acid like aluminum chloride to the diene and dienophile mixture, and this Lewis acid will coordinate with oxygen or any electron donating group. Then when it coordinates, you can see this will make sure you get like this canonical structure. So this canonical structure looks like allyl carbocation. Okay. So this is the energy difference between LUMO of dienophile and then HOMO of diene decreases mainly because of this type of canonical structure. So the strength of the Lewis acid also play a very important role, and as you know, the strength increases from iodine to aluminum chloride. So that's why you will see in many Lewis acid catalyzed Diels-Alder reaction, either aluminum chloride or derivative of aluminum chloride is used in Lewis acid catalyzed Diels-Alder reaction. Okay. So what does it do? Okay, for example, if you take isoprene and methyl acrylate, if you do uncatalyzed reaction, that is you don't add any Lewis acid and then you simply heat it, you get 7:3 ratio of 1,4 and 1,3 adduct. Okay, we have discussed in details. This is 1,4 and this is 1,3 adduct. However, if the same reaction is done with Lewis acid, that is aluminum chloride here, and you can see two major differences. One, the temperature has come down from 120 to 20 degrees. Okay, and this ratio also from 7:3 it has come down to 95:5. So the major product here is the 1,4 adduct and not the 1,3 adduct. So this is what Lewis acid can do when Lewis acid is added to the reaction mixture of Diels-Alder reaction. Okay. Normally when we talked about Diels-Alder reaction, we always say, so Diels-Alder reaction is part of pericyclic reaction, it does not need external reagents or so. It simply it can be done by heating or photochemical condition. Yes, one can do, but by addition of Lewis acid, one can bring down or you can reduce the number of hours taken for the reaction to complete. 2, it can also increase the selectivity. Okay. So let us see some more examples. So if you take again isoprene and then treat with acrolein, there is a possibility of mixture of 1,4 and 1,3 adduct, and we know that 1,4 adduct is the major product, and again here it is the ratio of 3:2 if you do this reaction only in refluxing toluene. But however, if you do this in Lewis acid, and the ratio significantly changes and it is in the ratio of 96:4 in favor of the 1,4 adduct. And if you take 1-methyl butadiene and then do the same thing, with methyl acrylate. Now you can see here the 1,2 adduct without catalyst is 9:1 ratio, but when you use aluminum chloride, it's almost completely in favor of the 1,2 adduct. So this is what Lewis acid can do. Though we discussed in details about when you have substituent in the diene and substituent in the dienophile, either 1,4 or 1,2 adduct should be the major product, but still you get 1,3 adduct in sizable amount, but the addition of Lewis acid will make sure that you get predominantly or almost quantitatively you will get the 1,2 and 1,4. And this is another very interesting example. You can see the methyl group and this alkene are cis to each other, and if you do the Diels-Alder reaction with methacrylene in the presence of methyl aluminum dichloride instead of aluminum chloride. The earlier examples we have discussed with the use of aluminum chloride as Lewis acid. Here we used methyl aluminum dichloride, and this in principle can give the cyclohexene, and as you can see here, this can be done at room temperature and only one product. The advantage is with respect to these two substituents it is 1,2, and with respect to these two substituents it is 1,4. You may recall the use of Danishevsky's diene and Ravel's diene in Diels-Alder reaction. There also you get 1,2 and 1,4 product. Okay. And likewise, if you take cyclohexadiene and then treat with methacrylene in the presence of another mild Lewis acid like indium chloride, you can get this bicyclo 2,2 octane system. Again, the endo isomer is the major product. And this particular example, if you see, particularly you can write a proper transition state, so that will give you, and that is nothing but what is being So the use of Lewis acid really helps in fixing the regioselectivity, and whether can it do further. For example, when you do a Diels-Alder reaction, you talk about chemoselectivity, you talk about regioselectivity, you also talk about stereoselectivity. Can all these three be controlled by the addition of Lewis acid? Let us see one example. So if you look at this dienophile, now first let us decide on the chemoselectivity. So there are two double bonds, this and this. Between these two, which double bond will undergo Diels-Alder reaction? So that is chemoselectivity. Second, you have two carbonyl groups, this and this. Which one will play as electron deficient group? Accordingly, the regioselectivity will come. Then the third one, that is stereoselectivity, that is mainly the endo product. Okay. So now the moment you add Lewis acid to this, then what happens? The Lewis acid will coordinate with this nitrogen as well as the oxygen. So you can draw a very nice transition state where the Lewis acid, the tin tetrachloride, can easily coordinate with nitrogen and carbonyl group. So when it coordinates, automatically this carbonyl group is more electron withdrawing, and that decides the regioselectivity. Okay. Then the question of stereoselectivity comes. As you know, when you have dienophile like this dienophile can approach the diene either from the top face or from the bottom face. In this particular example, what you can see is the diene is simple butadiene, and the dienophile approaches butadiene from the top face. So, if that happens, what you get is this product. So, you can easily write the product like this. So, this is how the product will be, and if you can redraw this structure, so this will be this product. Okay. So, the use of Lewis acid can control chemo, regio and stereo selective outcome of Diels-Alder reaction. Okay. And this is the key intermediate in the total synthesis of a highly toxic natural product called tetrodotoxin. Okay. And if you do not use Lewis acid, okay, the whole thing will change. Okay. If you do not use Lewis acid, then this double bond will undergo Diels-Alder reaction. Okay. This group will not play any role. So, by using Lewis acid, you can use this additional functional group to coordinate and make the other carbonyl group to play the regio selectivity. When you talk about Lewis acid, then the Lewis acids also are of several types, and particularly from the size point of view, some Lewis acids are small in size, some are really bulky. So, the bulky nature of Lewis acid, whether it will have any effect in the regio and stereochemical outcome. Okay. Yes, it plays an important role in the outcome of exo and endo selectivity. So, for example, if you take this diene having 3 substituents, okay, it has 1, 2, 3. So, 3 substituents on 4 carbon atoms, and then if you do a Diels-Alder reaction with this dienophile, and when you use different Lewis acid, the ratio of exo and endo isomers vary. For example, if you use BF3 ethyrate, okay, you get exclusively endo as the major product. From BF3 ethyrate, if you go to aluminum chloride, so aluminum chloride is slightly bulkier than BF3 ethyrate, then the ratio changes to 3:7, still in favor of endo product. However, if you use a bulky tripentafluorophenyl borane, okay, now the ratio completely changes. Now it is in favor of exo. Okay. Here I also have to tell you there are 2 electron withdrawing groups. One is aldehyde, the other one is ester. So, which one Lewis acid will coordinate? So, that also is very important. Okay. So, between aldehyde and ester, obviously aldehyde is the one which is more electron withdrawing. So, then the aldehyde only will coordinate with Lewis acid. That determines the stereochemical outcome of this particular Diels-Alder reaction. Okay. So far we talked about the use of Lewis acid in Diels-Alder reaction. Now, we will extend this to asymmetric Diels-Alder reaction. And when you talk about asymmetric Diels-Alder reaction, there are 3 ways one can carry out asymmetric Diels-Alder reaction or Diels-Alder reaction in non-racemic form. We discussed in details when you do a Diels-Alder reaction, the dienophile can approach the diene either from the top face or from the bottom face. So, that is why you get always racemic mixture. But in order to get a non-racemic Diels-Alder cycloadduct, you have 3 methods. One, you should start with a chiral diene or chiral dienophile, or in other words, you should have a chiral component attached to the diene or in the dienophile. So, that way you can differentiate. Okay. So, the approach of the dienophile to the top face or bottom face, one of the faces will be more facile, accordingly you will get 1 enantiomer more. Second, you can use a chiral auxiliary. I will come to that little later, what is chiral auxiliary, how chiral auxiliary plays a very important role not only in asymmetric Diels-Alder reaction, but also in other asymmetric reaction. The third one is you can also use chiral catalyst. So the difference between chiral auxiliary and chiral catalyst is, in the case of chiral auxiliary, you have to use stoichiometric amount of chiral auxiliary, whereas in the case of chiral catalyst, you have to use only few mole percent of chiral catalyst in Diels-Alder. So let us start with chiral auxiliary. Okay. So what is chiral auxiliary? See, chiral auxiliary is a homochiral group. It's a chiral compound, and this is normally attached to the substrate, which is not chiral. Okay. Chiral auxiliary is a chiral compound which is attached to the substrate, which is going to undergo reaction, in this case Diels-Alder reaction. Okay. So now what happens, as I said, the normal substrate without chiral auxiliary, when you do the reaction, it will give a racemic mixture. Okay. And if it is forming only one chiral center, then it will give enantiomers. Okay. These enantiomers you cannot separate. However, when you attach the chiral auxiliary to your substrate, which is not chiral, now when you do any reaction, in this case Diels-Alder reaction, so what will you get? You don't get a mixture of enantiomers. What you get is a mixture of diastereomers, because this reaction is diastereoselective. We know diastereomers can be easily separated. So what you do after this reaction is over, you separate the diastereomers. Okay, once you separate the diastereomer, then remove the chiral auxiliary by well-known methods. Now what you get is exclusively one enantiomer of that product. Okay, so this is a simple principle. There are a few chiral auxiliaries known, and I am showing 3. I will come back to that and then show more chiral auxiliaries which are routinely used not only in Diels-Alder reaction but also in other asymmetric reaction. So what happens? So what you do, you take any substrate and attach the chiral auxiliary. This is not a chiral compound, but this one is, because it has a chiral auxiliary. Then you carry out the reaction. Okay. The reaction, in this case Diels-Alder reaction, and now the Diels-Alder reaction is diastereoselective. So you get a mixture of diastereomers. So what you do? Separate the mixture and remove the chiral auxiliary. So once you remove the chiral auxiliary, you get your chiral auxiliary back, which can be reused. But the product, in this case Diels-Alder product, is one enantiomer, because you have separated 2 diastereomers, then only you cleaved the chiral auxiliary. Okay. So this is how one can easily do asymmetric Diels-Alder reaction by employing a good chiral auxiliary. We will discuss few chiral auxiliary based asymmetric Diels-Alder reaction in the next couple of minutes. So before that, how do you choose a chiral auxiliary? Because it's very important. There are so many naturally occurring compounds with chiral centers available, but you cannot choose all. So you have to choose a certain chiral compound as chiral auxiliary. So how do you choose? First, whichever chiral auxiliary you choose, it should give very high stereo control. Okay. So that means during the diastereoselective reaction, as far as possible, it should give only one diastereomer. Okay. So that you don't even have to separate. Okay. Just to cleave the chiral auxiliary and you get one enantiomer. So the chiral auxiliary which gives the highest percentage of a diastereomer is the most preferred chiral auxiliary. Then there are 2 more things which you have to look at while deciding on the chiral auxiliary. One, the chiral auxiliary should be attached to your substrate under very mild condition without affecting any other functional group. 2, after the reaction is over, it also should be cleaved under very mild condition, and particularly when it is cleaved, it should not racemize. Okay. So suppose if you are using a strong base, and that strong base should not epimerize or racemize your final products. Okay. And last but not least, the chiral auxiliary should be readily available. Okay. If not, it should be made in few steps with efficient in yield. Okay. And it is always preferred both enantiomers of the chiral auxiliary are available, because many times you use sugars, amino acids. Okay. So, in both cases, in the case of amino acids you get only L isomer, whereas in the case of carbohydrates you get only D isomers available from nature. Okay. So, if you can have both enantiomers commercially available, then it will be a good chiral auxiliary, so that you can get both enantiomers in the Diels-Alder reaction. Okay. So, there are many chiral auxiliaries known in the literature. So, let us talk about a few. The first one reported was from proline, and that was reported by Yamada in 1969, and 6 years later Corey used a very famous 8-phenyl menthol, and this was prepared from puligone, another commercially available monoterpene. Then Dieter Hinters a year later, he prepared and used this very interesting hydrozones called SAMP and RAMP hydrozones, not only in Diels-Alder reaction but also in many asymmetric reaction. And 5 years later, Evans used the most widely used chiral auxiliary called oxazolidinone. So, these oxazolidinones are prepared from amino alcohols, which in turn are prepared from commercially available naturally occurring amino acids. And 2 years later, Wolfgang Uppolzer from University of Geneva, so he used sultam, which is prepared from camphor sulfonic acid. So, this also is a very good chiral auxiliary and could be successfully used in many asymmetric reaction. Helmchen a year later, he used camphor based amino alcohols as chiral auxiliary. And then Kunz in 1992, he prepared again oxazolidinone from sugars, and Arun Ghosh in 1998, he prepared another interesting oxazolidinone derivative derived from Indian amino alcohols. So, these are some of the commonly used chiral auxiliaries, and what we do, we discuss a couple of them. One Corey's 8-phenyl menthol, the other the Evans oxazolidinone in asymmetric Diels-Alder reaction. So, this 8-phenyl menthol, as you can see here, so this is the hydroxyl group where you attach the dienophile. Say for example, if you take acrylyl chloride and attach with 8-phenyl menthol. So, now in this intermediate, what you have seen is you have attached the dienophile to the chiral auxiliary. Okay, that is the first step. So, once you have attached the chiral auxiliary, now you can see this double bond is blocked by the phenyl group from one face. Now, the diene, if it has to approach this dienophile, it can approach this dienophile only from the front side, and back side is blocked by the phenyl group. Okay. Now, next, when you look at this dienophile can exist in S-cis conformation as well as S-trans conformation. Okay. If it is in S-cis conformation here, so this double bond is coming out of the phenyl group in the background. So, in the case of S-cis, there is a likely possibility that the diene can approach from the front side as well as from the back side. Okay. So, how do you control this to be only in S-trans conformation? Yes. So, this is where you have to add Lewis acid. So, when you add Lewis acid, in this case aluminum chloride, because of this bulky aluminum chloride, this forces the double bond to go to the other side. From the cis, it comes to the trans. So, now in the Diels-Alder reaction of this chiral auxiliary attached dienophile reacts only in this conformation. Okay. Now, again there are two possibilities. You have the chiral auxiliary attached to the dienophile, and the dienophile coordinates with aluminum chloride. Now the diene has to approach. Earlier we have discussed that diene can approach the dienophile from the front or back side, or from the top or from the bottom. Okay. So now since the back side is blocked, it will come only from the front side. So that way it is clear that you get one isomer. But what about exo and endo? Okay. So there are two possibilities. One possibility is the diene coming like this. That means in this transient state, the carbonyl group is under the diene. That means this will lead to endo product. Okay. Then there is another possibility that the diene is coming like this, where the carbonyl group of the dienophile is away from the diene. That means that will lead to exo product. So we know between these two, the endo product is the one which is most preferred. So what happens if this reaction takes place in this transient state? So what we get is this product. I will leave it for a few seconds. So then you can see this is what you get. So once you have this, you can cleave the chiral auxiliary with lithium-benzyl oxy compound. Okay. Now you get the corresponding ester. So this product can be cleaved with this reagent so that you get ester and also release the 8-phenyl menthol. Okay. So this is how you can see Corey cleverly used 8-phenyl menthol as the chiral auxiliary in 4+2 cycloaddition reaction. So now we will move to Evans chiral auxiliary, which is called Evans oxazolidinone. So here this oxazolidinone is prepared from the corresponding amino acid. So now you can deprotonate this NH and then attach the alkyl chloride. So now you can see here you have successfully attached your dienophile to Evans oxazolidinone. Then you add the Lewis acid, and that will give this intermediate. Okay. So once you have this intermediate, when the diene approaches this dienophile, this benzyl group, okay, it's a bulky benzyl group, blocks the approach of the diene from the bottom face of the dienophile. So the diene can only come from the top face. If that is the case, what you get is this product. Again, you can easily cleave the chiral auxiliary, and that will give the corresponding benzyl ester. One can also reductively cleave so that you will get the corresponding primary alcohol, or you can also oxidatively cleave, you can get corresponding carboxylic acid. So all these cases you can see you will get only one enantiomer as the major product. So this has been successfully used not only in the synthesis of a terpene called alpha terpenol, but there are many total synthesis of natural products where this chiral auxiliary has been successfully used. Likewise, you can also use cyclopentadiene as a diene, and a similar transient state. You can see here what is the difference is. There you have used benzyl group, here we have used isopropyl group, and in the dienophile also we have one extra methyl group, and you can see this is the transient state. Okay. So now the diene has to come only from the top side, not from the bottom. So that will give you this transient state, and after removing the chiral auxiliary, you get this bicyclo 2-to-1 system, and also you recover your chiral auxiliary. These two are very nice examples of using chiral auxiliaries in Diels-Alder reaction. How about chiral catalysts? Yes, one can also use chiral catalyst, and this was designed by E.J. Corey. So he has also used amino acid. It's always good to see a lot of amino acids available. So Corey used another amino acid to make this chiral catalyst, and you can see the reaction being done at -78, And if you look at the transition state, so this is the transition state where the electron rich oxygen coordinates with borane of this chiral catalyst, and this cyclopentadiene can come only from the exo phase. So that is how this particular reaction gives mostly the exo products. Okay. And he also successfully used this in the total synthesis of prostaglandin. This particular asymmetric Diels-Alder reaction he has successfully used. For example, this should be converted into ketone, that is if you take cyclopentadiene and then do ketene equivalent Diels-Alder reaction, you will get a bicyclo 222 non-enone. So for that, what he has done, this aldehyde he treated with hydroxylamine to get oxime, and this oxime if you convert into the corresponding tosylate, then it can undergo elimination to form cyanohydrine, and that cyanohydrine if you treat with base, it will give a corresponding ketone. Okay. So what we discussed today is about the use of Lewis acid in Diels-Alder reaction. Then we extended that in asymmetric Diels-Alder reaction, where chiral auxiliaries from Corey's group and the Evans group, how these two chiral auxiliaries have been successfully used in asymmetric Diels-Alder reaction. And we also briefly talked about the chiral catalyst, boron based chiral catalyst in asymmetric Diels-Alder reaction. Okay, I will stop here. So far in the last 9 lectures, so we have discussed quite a bit of 4+2 cycloaddition reaction, and the next lecture we will move from Diels-Alder reaction to 1,3 dipolar cycloaddition reaction. Okay, thank you.